Very good evening to our Madam Hemyza. My name is Jock Dison. So today, me and my friends Hamizan will present our building cross-section report. A deep foundation is a form of foundation that is erected very below the surface of the ground and displaces structural loads deep into the earth. Such a foundation often has depth to breadth ratio larger than 4 to 5. The foundation offers the having less sites restrictions and advantages of supporting more favorable soil conditions. A deep foundation is more difficult and expensive to build than a shallow foundation. However, a deep foundation is likely to be the best choice when coping with poor soil conditions at shallow depths, significant design loads, and site limitation. Every building often has several spread of foundation. It is to ensure that the column weights are passed to the ground directly. Deep foundation also provide advantages over shallow ones, which is being appropriate for challenging soil conditions and having less site restrictions. Rotary drill press in construction offer the ability to modify instruments for cutting or digging and a better suit to soil conditions or certain type of auger. It can also include large columns inside the mound to encourage top-down bleeding. LDP can install at much larger depths and has a higher load capacity than conventional piling method. Rotating a casing into the earth to support granular or pure ground is basically how rotary board spars are built. The pass bar is then removed using an auger, bucket, or coring device linked to a telescopic caliber. As we can see, the majority of ground conditions through soft ground supported by temporary casing to high-grade, extremely hard rock core into the open hole procedures will call for the use of rotary piling. Benefit to using rotational piling such as decreasing ground disturbance and vibrations, which lowers the risk to nearby structures and property. With the aid of measuring tape and marking made using control points, setting out drawing from a consultant, the drilling location needed to be marked and pegged by a contractor surveyor. The surveyor then used theodolite equipment to record and coordinate the reduced level for each spot. Prior to start of the boring work, each pile position that was assessed was shielded from disturbance. Then two reference sites were set up equally spaced apart and at least 2.0 meters from the center of the three piles. Following that, a pilot hole with drill at the pile site and drilling eccentricity and alignment were confirmed. In order to stop soft soil from entering the drill hole, a temporary casing was placed into place using a service crane. The casing was put in place during the installation procedure using a vibro hammer. During the installation procedure, the personnel verified the vertical correctness of the casings. Crawlers were used to construct a platform around the casing after installation. The soil inside the casing was carried out as the polymer was being poured into the drill pile using a rotary bar and an auger. By utilizing augers and drilling a bracket, the drilling process continued until the beginning of the rock hard level. To monitor changes in the soil layer to be studied, soil samples were gathered every 3 meters of depth. Every soil layer deep in the board pile was examined. Once at the desired depth, the trash and remolded material were removed. Using a cleaning bucket and rock sample were collected for analysis. Sonic caliper measurement was used to determine the hole depth and diameter. For the polymer process, high turbulence mixer were used to combine the polymer bentonite. Because bentonite can dissolve in water, it was used. The board hull is then stabilized by using bentonite as a drilling fluid. Throughout the tedious process, the bentonite must be kept as high as possible inside the casing and much above the groundwater that is already there. Prior to reusing the bentonite after boring, cleaning was done using a cleaning basket. The trimmer pipe to which the submersible turbine pump was attached was lowered till it reached the bottom of the drill hole. Following that, the bentonite was removed from the bottom of the borehole and recycled using a comparable rescale device. Continue until the bentonite began to rise from the base. Next, the installation of steel cage. The steel cage was ready to be put within the shell. Steel cage dimensions, can and length must all adhere to contract drawings and specifications. To prevent injuries, the reinforcement cage must be constructed in the laydown section. Next, to facilitate handling, lifting, and installation without causing permanent deformation, the cage was fastened to the service crane. Workers helped the steel cage fit into the drill hole after the service crane hoisted them. Section by section, the trimmed tube was then inserted. In order to prevent washout of cement from the mix due to turbulent water contact with the flowing concrete, a trimmer was employed to pour the concrete underwater. For the next method, concreting work. Before pouring fresh concrete into a drill hole, it must undergo a concrete slump test to determine its consistency. The purpose of this test was to determine whether freshly produced concrete was workable and so flow easily. Following the completion of the concrete slump test, the cube test was corrected. It was carried out to gauge concrete compressible cube strength and boost trust in its quality. After the slump test, the contractor gave its approval. The concrete was poured using the trimmed method to cover every part. After each piece of concrete had been concreted, the trimmed tubes were removed by checking the depth of the concrete level once more. After each concrete truck emitted, the borehole concrete level was measured, and a graph was made against a theoretical value. All finished piles were temporarily barricaded, and suitable substance was used to backfill the ground level. For the last method, removal and cleaning. Using a vibro hammer to top off the extruded steel with concrete, the temporary casing was partially removed. To maintain the building site free of any danger, all the spoil from pile at the boring area were cleared. For the subsequent marking point, the same process was used.
Assalamualaikum and salam UITM di hatiku. I am Muhammad Hamizan bin Hasnol Badrian from AP 116 4A. Now I am going to present about the problems and solutions that we encountered for this basement construction. Problem number 1. Blow count for bearing piles abruptly changes or decreases. The solution is, using boring, the soil condition must first be evaluated. For piles that permit internal inspection, the light needs to be reflected into the pile too, and signs of deterioration need to be looked for. Third, dynamic measures should be taken to assess the issue or contemplate pile extraction for piles that cannot be internally inspected. Problem number 2. Blow count is slightly lower than expected. The solutions are: firstly, determine the driving force for the capacity reduction as well as the preparation factor. Secondly, the performance of the hammer should even be examined because it might be better than anticipated. The third problem, lateral movement of previously installed pile when driving new pile. The solutions are: the current pile will move due to the movement of a new pile during the land transfer. Redriving the installed piles, switching the order in which the piles are installed, or pre-drilling the pile positions are some potential ways to minimize ground movements. The fourth problem: piles are driving out of alignment. The solutions are: if poor hammer pile alignment management is the cause, a pile gate, template or fixed lead system may help to preserve alignment tolerance. Second, when there are near surface impediments or steeply sloping bedrock with little overburden material, the alignment will also be disrupted. Problem number 5. Deep pile obstructions are encountered. If deep impediments are discovered while driving, an engineer must be contacted for a corrective design. The ultimate bearing capacity of piles hitting impediments will need to be decreased based on the likelihood of pile damage and the characteristics of the soil matrix support. Possibly, more piles are required. Problem number 6. The last problem. Block count is significantly lower than expected. The solution is: when the block count to drive the pile is lower, it is necessary to review soil boring first. If soil boring does not reveal soft layers, the pile below grade may be damaged. If the pile was spliced, review the fill procedures and splice detail again for potential splice failure. Now we have come to the conclusions of this presentation or this report. We can conclude that there are difference of methods that used in installation of deep foundation. The method used is new and can be distinguished with other methods when it produces minimum vibration, making it ideal for areas requiring low vibration and noise pollution, and it is also can even be installed with minimal noise, making them ideally suited to use in populated densely areas. Besides, the time it takes to construct it is also shorter. There are also some problems in construction, and it is quite difficult to solve because need a complex thinking to solve the problems. However, all these issues can be solved by having a good construction team. Okay, that's all from us. Thank you for listening to our presentation. Salam UITM di hatiku.